Section 2.5, the precise definition of a limit. We've worked with limits for this entire chapter, but we've used a very intuitive and geometric definition for what a limit is. In this section, we're going to get pretty rigorous and talk about something called an epsilon delta proof, and this is the formal definition for a limit. The first thing that we're going to talk about is something called closeness. Many of us are very familiar with the English language, and we know what it means to be close to something. But if you hang out with mathematicians enough, you'll realize that they need precise definitions for everything. So if I say close, they would say, what do you mean by close? So let's define that for them. The first statement that we use for closeness says the absolute value of f of x minus L needs to be less than epsilon. And basically, we're going to interpret that as a distance between the function value and a number L. And we're going to make that distance smaller than some number epsilon. The second statement that we're going to use for closeness says that the absolute value of x minus a needs to be squeezed between 0 and delta. So delta is also a number greater than 0 that we're going to use for that inequality, and we'll interpret this to say as long as x is not equal to a, we're looking at the distance between x and a. That's what x minus a is, and we want that distance to be less than delta. The function that we have on the screen is some kind of cubic function, so let's not worry about the definition there. It's just a generic f of x function. We can see that it's nice and continuous. And I also have a point A marked on the x-axis. This is the value that I'm allowing x to approach in our limit notation. So as x approaches a, the blue point on the x-axis represents that a value. If I were to plug that point into this continuous function, it would appear as the point a, comma, f at a. And then the output, that f at a value, that's essentially L. So for a continuous function, the a is on the x-axis, the L is on the y-axis, and it's essentially the output of the function for whatever value of a we plugged in. Now that we know what L is, we can talk about these statements, these closeness statements. The first one, absolute value f of x minus L. The distance between f and L is less than epsilon. We're going to manipulate that algebraically. And the first thing that we need to do is break open that absolute value notation. And that basically says that it's equivalent to having a compound inequality where we have epsilon with a negative on the smaller side and epsilon as a positive for the larger side. So we dropped the absolute value bars, added a second inequality to say that negative epsilon is really the smaller bound now that we're not making this an absolute value. Next, I'm going to add that L to get rid of the L in the innermost part of this inequality. I'll add L to all three parts of the inequality so that now I have negative epsilon plus L on the small side, epsilon plus L on the positive side, the bigger side. And f of x is by itself in the middle. And that's useful because now we can kind of visualize what that would be on the graph. I'm going to use this horizontal strip where I'm centered at the point L. That's my f of x value from the output of plugging a into the function. And I'm allowing myself to go above that, L plus epsilon. I'm allowing myself to go below that, L minus epsilon. So essentially here, epsilon is the distance between L and that dashed line that you're seeing. This is epsilon. This is also epsilon. So the width of this little strip is actually 2 times epsilon. Any function value that's between these two strips is going to satisfy that first closeness condition. So everything from right above this dashed line all the way along our curve and all the way up here, all of these values of the function satisfy this first closeness condition. Anything outside of here does not satisfy. These points are outside of the strip, therefore they're not considered to be close based on that definition. I can let that epsilon shrink if I want to, which would essentially shrink the horizontal strip that you see in blue. So as epsilon gets smaller, that strip gets skinnier. Next, let's talk about that second statement of closeness that involved delta. First thing we'll do here is break open the absolute value bars, and we'll do that by making positive delta the larger side, and then we're going to have a negative delta on the smaller side. And then after that, we'll add a to all three parts of the inequality so that we've isolated x in this inequality, and we're going to make a strip that goes vertical this time out of the values negative delta plus a and delta plus a. And we see that here on the screen as a vertical strip that's in red. We have ourselves centered at the point A, that's the value x is approaching, and we can see that on each side of A, there's a little space, that's our delta. So this width from side to side is equal to 2 delta, since delta goes on both sides of the value A. And the same way that we had epsilon shrink, which shrunk our horizontal strip, we're going to let delta shrink to shrink that vertical strip. So this is what we mean by closeness. Again, any value that's inside of these vertical dashed lines satisfies that second condition of closeness. Anything outside of those are not considered close. They don't fit that inequality. Now let's take a look at the actual definition of the limit, the epsilon delta definition. F of x is going to be a function that's defined for all values of x. That means we're not talking about a function that has issues in it like the logarithmic functions or the radical functions where you can't plug negatives into it. We're defined for all values of x on an open interval containing a. So that just means the function is there. That's all we're saying there. The function is there. And we're going to pick L to be a real number. That means we're not going to use infinity for limits here. Then the definition says that the limit as x approaches a of the function f has to be equal to that real number L. If for every epsilon greater than 0, so epsilon is going to be some positive number, there exists a delta greater than 0, such that the two closeness conditions are met. Now let's read that really carefully. This says every value for epsilon, which means there's no restriction other than epsilon has to be positive. The next one says there exists a delta. That means that there only has to be one delta that works. Maybe it's possible that there's more deltas that work, but there exists means that there could be as few as one, but there will always be at least one. So what we're going to do is read this as, if I can find the right delta, then I can use whatever epsilon I want. And with those two values for delta and epsilon, our closeness conditions will always be satisfied. Meaning the distance between F and L will be smaller than the epsilons that we use, and the distance between X and A will be positive, but smaller than delta, whatever we picked. Let me try to illustrate that for you here. I'm using the sliders to change the values of epsilon and delta. And we can see that if I pick a delta that works and an epsilon that works, then the function inside the box turns green. But if one of those values is out of line, then the function inside the box turns red. So I'm picking delta and then I'm checking that all of the epsilon values work. And for the first few combos that I use, I can find a couple epsilons that work for each delta, but I can't find that all epsilons work until I shrink delta very small. So let's watch that one more time. This combo does not work, no matter what I use for epsilon. But if we shrink delta, ooh, that works for epsilon at 2, but if I move epsilon to be smaller, it fails. Shrink delta again. This time the epsilon works for more numbers, but it still fails if epsilon is too small. We try it again with a smaller delta. We still see that there's values that don't work until I get the smallest value of delta, and then all of the values for epsilon will give us a green portion. So we just needed to find a very small delta to make that one work. So what I'm saying here is that we want to find the one delta, at least one, that will allow any epsilon to create a box that completely contains the function. So here, the box that we've created is made up of this tiny little strip. So it's a rectangle, not really a box, but all of the function values that are contained inside of this box that I've colored in red satisfy our closeness conditions. You might think to yourself, well, what would it mean to not be able to find a delta? It sounds like you just need to find a small enough delta. And for continuous functions, that's true. But what you can see on the screen here is that I don't have a continuous function. And this is where a limit fails. If you remember, discontinuities are what break limits. So let's take a look what happens with playing with the different values of delta and epsilon. So at delta equals 1, epsilon works if it's big enough, but once we start to shrink it, it fails. Same if we shrink delta here, the smaller epsilons don't work. And I could shift that L point. Notice that because the function has a jump, I could use any of the points between these two curves as my center point for L, but it doesn't matter because no matter how small I make delta, there will still always be some epsilon value that makes it to where that horizontal strip can't contain all of the function values. Let's watch it one more time here. Notice that every delta that I pick, I can find an epsilon that ruins everything, meaning that green portion turns red. And that's because of how far apart the function lines are. I can't shrink my strips to make it to where all the function values are within that horizontal strip. Now let's talk about how to prove that a limit exists for a specific function. Now these delta epsilon or epsilon delta proofs, they're not going to help you find what the limit is equal to. What they do is guarantee that what we're saying is correct. We're guaranteeing that the limit is equal to that number. So typically the way this works is you start off with a statement. So this is different than what we've been doing because in the other examples, we try to calculate that value. Here it's going to be given to us. But the exercise is to prove that that statement is true. So to prove this statement is true, we will always start by saying let epsilon be greater than 0. That's something that has to be true. We start with that assumption, and then everything after that will follow. The next thing we're going to do is find delta. Now we know delta needs to be greater than 0, but we're going to be more specific about that delta. Remember, there might only be one delta that works, so we want to find the right one. We're going to talk about this, so we're going to take a little turn, and we're going to talk about how to find delta in two ways. We're going to find it geometrically first, And then we're going to go through and find it algebraically. I've got a different function on the screen. So we're taking a step aside from that last function that we were looking at. And what I'd like to do is talk about what delta is and how we find it. So in the video that I've got on the screen, I want you to look at that horizontal strip, the blue strip. That's the interval between L plus E and L minus E. Sorry, epsilon, not E. It's that interval on the y-axis. And I want you to pay attention to where those blue dashed lines intersect our function, the black curve. Now, what I wanted you to notice in there is that the function is intersecting those horizontal strips in two spots. And I've got two pictures of that on the bottom. Each of those intersection points can correspond to a value on the x-axis. We're going to pick the value that is smaller to define our delta box. What I mean by that is we have this value, so this distance away from A, that causes that intersection on the left. That could be the delta, but if it were, then when I copy it to the other side, notice that there's a section of function that is not fitting inside of the box. So this whole portion of the function, it's within that delta range that we thought would work, but it's outside of the box that we're using, we're creating using epsilons and deltas. So the bigger delta is not the better option. Instead, we want to pick the smaller delta. So if we were to use the smaller delta, the smaller distance between the A value and the red dashed line, and we use that to make the box, then we're going to fall short of that left intersection point, but that's fine because when we create our box of epsilon and delta values, everything inside of that box contains our function. All of the function values are within there, whereas on the other piece that wasn't true because of what was happening right here. It was on the correct side of the line, but those function values weren't inside of the box like they are in the picture on the right. So again, we're going to watch that video one more time, and I want you to see the relationship between the horizontal strip, how it intersects the function, and then follow those values down to the x-axis. We're going to see that as long as we use the smaller delta value, all of the function values will appear inside of the box. Okay, now we're ready to talk about finding delta algebraically. And we're going to use this example to illustrate how to do that. So we're looking at the limit for the function 2x plus 1. We're allowing x to approach 1, so x is approaching 1, which means a is equal to 1. And we're saying that that limit is equal to 3, so L is equal to 3. And for the epsilon delta definition of a limit, we have our three assumptions: that epsilon is greater than 0, also that the distance between my function and the limit value needs to be smaller than epsilon, and then lastly, we know that the distance between x and the value a that we're approaching is smaller than delta. So if we plug our function into that second definition, then we find this statement. that 2x plus 1 minus 3 inside of the absolute value bars needs to be less than delta. We're going to start there and simplify. Now, we have parentheses in this original notation, but that's just to highlight what the function is. They're not doing anything, so we can drop them. It's not going to change the value of that expression. However, it will make it easier to show that we can combine these two numbers, 1 and -3. So let's go ahead and do that to simplify. Then from here, there's not much I can do, but I can factor out that 2. And then I can think about the fact that 2 is a positive number, so the absolute value of 2 isn't really doing anything to it because it's already positive. So I can factor the 2 outside of the absolute value. Now, I can't take x minus 1 out of the absolute value bars, and that's because we don't know if x minus 1 results in a positive or a negative, so we'll have to keep those there. And then at that point, we realized, oh, there's nothing else we can do. That's as simple as it gets. So we move on to our next assumption. This assumption tells us that the absolute value of x minus a is less than delta. Well, our a is 1, so we can make the assumption that the absolute value x minus 1 is less than delta. And if that's true, then I can replace my equal sign that I have here with an inequality and replace the absolute value of x minus 1 with delta. And then I'll just bring down this factor of 2. So following the chain of simplification, we started off with the function minus the limit, and then we simplified the best we could to where we got 2 times the absolute value x minus 1. And then instead of writing equal sign, we have to replace with an inequality so that we can swap out the absolute value of x minus 1 with delta. And then from here, we want to make sure that all of this is less than epsilon. So what we'll do is think about what delta would need to be so that we can replace this right side of the equation with epsilon. Well, we have 2 times delta, and we want to replace that with epsilon. So let's solve that for delta. This says we should use delta equal to epsilon over 2. So if we make that substitution, I can put an equal sign here and replace delta with epsilon over 2. My 2's will divide off, and I'm left with epsilon. And if we read through that very carefully, we can see that our original function minus the limit is less than epsilon. So we have our function minus the limit, our less than inequality, and then epsilon. All of the other steps are kind of just leading us up to that big finish there. Let's go through that one time really quick so that we can see how smooth this can actually go. After all of that algebra, we know that we need to choose delta to be epsilon over 2. Because if we pick that to be the case, then we can use the assumptions and everything that follows will give us the result that we want. And there we have it. The distance between the function and the limit value is less than epsilon.